Hello, my name is Nate Gillespie, and this is a pre-recorded presentation for the 2022 meeting of the Society for Mathematical Psychology. The question of how the physical and psychological dimensions of perception are related has long been studied across many fields of cognitive science. Some examples of such studies include investigations on how exemplars enable categorization of stimuli that vary across dimensions, how similarity between stored exemplars impacts episodic recognition, and how complex visual events are segmented in ecologically valid settings. A common thread here is the issue of how people encode static or dynamic events with varying degrees of featural overlap. In the present study, we used novel auditory stimuli to begin building a bridge between different areas of previous research in order to address this question. Audition was chosen because it allows for tight control of stimuli in experimental settings, the ability to combine or isolate sounds, and is naturally extended in time. Thus, our goal was to create a set of stimuli that can be combined both within and across time to mimic the complexity of the structure of natural events. In pursuing this goal, we aim to begin understanding how simple auditory events combine in order to generate more complex phenomena like speech and music. To address the question of how featural overlap impacts the perception of sounds, we constructed a set of 10 electronically generated auditory stimuli which varied in featural similarity along a single sound quality, timbre. Timbre encompasses a range of associated auditory properties other than pitch, duration, and loudness, and allows for sounds to be distinguished from one another. It is somewhat analogous to the visual textures associated with different materials. Consider, for example, the sound of a violin versus the sound of a piano. Both instruments might play the same note, but produce different sounds because of each instrument's unique timbral features. We chose to study timbre because it is an aspect of sound that is not strongly influenced by pre-experimental experience. Every sound that we hear consists of sine waves at various frequencies combined in different patterns. The lowest frequency in a given combination, that is, the fundamental, is what we perceive as that sound's pitch. The frequencies above the fundamental contribute to that sound's timbre in various ways. Natural sounds consist of both harmonic overtones, which are whole number multiples of the fundamental frequency, and non-harmonic overtones, which are not whole number multiples. We therefore included in our set sounds that contained both harmonic and non-harmonic overtones. To construct the sounds in our stimulus set, we generated sine waves at various frequencies above a 200 Hz fundamental. For example, one sound contains sine waves at 200, 400, 600, 800, 1000, and 1200 Hz, while another contains sine waves at 200, 400, 600, 800, 1000, and 1015 Hz. This procedure allowed us to hold pitch constant while manipulating some key aspects of timbre. Thus, we created a set of sounds with a range of featural overlap, from 11% timbral similarity on one end of the spectrum to 100% timbral similarity on the other. In other words, we manipulated the physical features of various sounds in order to assess how people relate those sounds to one another during encoding. A subset of 7 sounds was selected from our stimulus set and used in a similarity rating paradigm during an online survey on the platform cognition.run. We first created a list of all possible pairings of each of the 7 sounds, resulting in 21 total sound pairs. Then, we played these pairs in random order. Sounds in each pair were played sequentially, for 5 seconds each. The order of presentation within the pairs was also randomized. After the second sound in each pair was played, participants were prompted to make ratings about how similar the 2 sounds were using an unmarked Likert scale ranging from not at all similar to completely similar. An example of one sound pair is as follows. You may wish to adjust your volume if you're wearing headphones at this point. Following this procedure, we collected data on sound pair presentation, similarity ratings, and response times, along with responses to demographic questions on age, gender, race, hearing ability, and musical expertise. We also asked participants about their strategies during the similarity ratings task. Survey completion took approximately 10 minutes and was completed by 66 undergraduates at the University of Albany, SUNY, in exchange for course credit during the spring of 2022. Participants were 33 men, 32 women, and 1 gender nonconforming individual. Participants' ages ranged from 18 to 30 years old. To analyze these data, an R script was designed to sort sounds according to people's similarity ratings in multidimensional space. This script used a non-metric variation on a classic multidimensional scaling, or MDS, solution, which accounts for individual differences by assuming that everyone represents things the same way psychologically, but that different people give more weight to various dimensions in similarity space. Our MDS solution is depicted in the scree plot shown here. MDS finds a psychological representation of a set of stimuli that minimizes stress, roughly the difference between people's perceived distances between stimuli and the distances between stimuli in psychological space. With more dimensions, it is always possible to achieve lower stress. So to find a balance between low stress and overfitting, we looked for the elbow in the scree plot, where stress stops diminishing rapidly and starts diminishing slowly. 3 dimensions were sufficient. The results from this analysis showed a clear split in similarity along a single dimension. This split corresponded to sounds that contained upper frequencies that were whole number multiples of the fundamental, and sounds containing upper frequencies that were not. The plot of the MDS solution shown here indicates this split with 2 red circles. Sounds on the left of the diagram contained natural overtones, while sounds on the right contained non-harmonic overtones. Sounds in each of these categories are quite distinct from one another, as stimuli containing non-harmonic overtones sounded distinctly rougher than stimuli containing only natural overtones. These findings suggest that the coarseness or roughness of a sound is an important psychological dimension along which people differentiate auditory events. We also found more subtle splits in dimensions 2 and 3. Although these did not admit simple verbal labels, analyses of various spectral qualities of the sounds provided some insight. One such quality, the spectral centroid, appeared to explain some of the variation along dimension 3. The spectral centroid is essentially the center of mass of a given spectrum and indicates the frequency around which the energy of a particular sound centers. In previous research, it has been correlated with the perceptual dimension of a sound's brightness. This is a spectrogram of sound 5 from our study. It shows the frequencies contained in sound 5, one of the non-harmonic overtone sounds, plotted over the course of 5 seconds. The white line in this graph shows where the spectral centroid is located throughout the signal. In this case, the center of energy for the spectrum appears to converge around 1265 Hz and remains there for the duration of the clip. I will now play the sound. In our study, sounds with greater spectral centroids had higher similarity along dimension 3, which is depicted in the displayed figure. This pattern held true for both sounds that contained natural overtones and sounds that contained non-harmonic overtones. For example, sounds 7 and 9 had spectral centroids that converged around 1350 Hz and 1360 Hz, respectively. In comparison, sound 5 had a spectral centroid of approximately 1265 Hz. Similarly, sound 2 had a spectral centroid of approximately 1165 Hz, while sounds 1 and 4 had spectral centroids of approximately 928 Hz and 1020 Hz, respectively. One notable exception to this trend, however, was sound 3, which had a spectral centroid of 1016 Hz, yet was rated as highly similar to sounds 2 and 7 and 9 along dimension 3. This trend suggests that brightness may be a relevant feature during encoding. The variation along dimension 2 was not well explained by spectral analyses. However, our results suggested that this dimension may be related to expertise. This figure displays the words the participants used to describe their listening strategies during our study. The size of each word corresponds to its relative frequency of use across all participants. We found some correspondence between musical experience and participants' abilities to describe their strategies for comparing sound pairs. For instance, 2 participants with more than 10 years of experience described using strategies like listening for differences in the quote, overtones and undertones of various sounds. Another participant with 5 to 10 years of experience indicated that they attempted to differentiate sounds by identifying the quote, background and higher frequencies involved. In contrast, participants with less experience tended to use strategies that relied on comparing the pitches of the 2 sounds. Since pitch was held constant across all the sounds in our stimulus set, it may be that participants with less musical experience are unable to perceive features like number of overtones, while participants with greater expertise can use such features to aid in discrimination. This could indicate that certain kinds of similarity between sounds may only be perceivable to those with more developed aural skills. If so, it might be possible that 2 sounds which have a large degree of featural overlap might be encoded differently as a function of a listener's experience. To further investigate the question of how the physical dimensions of sound correspond to the psychological perceptions of sound, future work might leverage these stimuli in recognition paradigms in order to reveal how similarity affects encoding. Manipulating the presentation order of these stimuli in various recognition memory tasks may help shed light on whether timbral features are combined in an unlimited, limited, or mutually facilitative fashion. For example, it could be interesting to combine sounds sequentially as follows. Or play them simultaneously like so. Given previous research investigating the coupling between item similarity and associative strength, these stimuli can be used to construct combinations of sounds that vary in similarity to test different predictions of models of associative encoding, like the 2020 model of Cox and Chris. Of note, since the Cox and Chris model was only applied to static stimuli presented simultaneously, these auditory stimuli enable us to ask a new question, namely, does similarity between items affect associative strength only when they are processed at the same time, or does it matter when they are presented sequentially, too? To summarize, the present study investigated how overlap of timbral features impacts the psychological perception of similarity between sounds. Our work constructed a novel set of auditory stimuli with varying degrees of timbral overlap and used multidimensional scaling to reveal that similarity between these stimuli is perceived along 3 dimensions, 2 of which appear to correspond to roughness and brightness. Our hope is that this study represents a step toward a more integrative understanding of how aspects of the individual structure of dynamic events can accumulate and create knowledge and meaning over various timescales. Thank you for your time.